So, lesson 3. With that said, we're going to start off with some thought experiments. Once again, you're going to have to vote. You ready? Here's a collision. I drew a little truck, I drew a little car. You know what? Let's make it a big 5-ton moving van and a little Austin Mini Cooper. Okay, there's our contrast. In the collision below, which vehicle experiences the larger force? The truck, the car, or both the same? Once again, you're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So in the collision below, which vehicle experiences the larger force? Who says, Mr. Dewick, the truck is bigger. It's got to be the truck. No one. Who said, Mr. Dewick, the car is going to get creamed. It's got to be the car, Mr. Dewick, the car. The car, Mr. Dewick, the car. No one. Really? Who says both the same? Wow. My other two classes, I had about a 50-50 split between B and C. Now, C is right. Why? Rebecca, I read your lips. Come on, say it loud and proud. Okay. I got into an argument with my block D, but Mr. Dewick, wait a minute, how can the force be the same? The car's getting creamed. What you don't want to do is mix up damage with force. And in fact, what we're going to talk about today, John, we're going to get even more specific in terms of a collision. What is it that causes the damage? And in fact, the next question I asked here, example 2, I said, so why is it that the car and the car driver are almost always so much worse off as a result of this collision? And that's for you to think about. Any thoughts? You agree with me, Trevor, they have the same force? Okay, you know what? I'm going to write down right here, and you can as well. Same force. But let's break that down. F equals what? MA. Are the masses the same? Oh. So if they have the same force, what can you say about the truck's mass? Big or small? So if it has a really, really big mass, it's going to have a small acceleration because same force. Compare that to the car. And Haley, this is what I wanted to say, I mentioned earlier. What actually does damage, it's the acceleration. It's the acceleration. I have a t-shirt, I'll probably wear it once the weather gets warmer. It says, it's not the fall that kills you, it's the delta V over T, which is the physics symbol for acceleration. Okay. If you really want to take it to its extreme, Sarah, imagine a Greyhound bus and a big ladybug hitting each other. What's the relationship between the two forces? They are the same. The Greyhound bus has such a big mass that for all intents and purposes, it has no acceleration. There's probably technically, Courtney, an acceleration like 0.000000000, whatever. The ladybug has such a small mass that it accelerates into a... Okay? Yeah? So you agree with me that forces are the same? I'm going to say another thing as well. I'm going to argue that in a collision, not only are the forces the same, but the time is the same for both objects because they're part of the same collision. I'm going to make them stick together and not bounce apart and not have weird stuff happen for our simple case. I need to give you a terminology. A closed system is one that's cut off from the outside world. What this really means, there's no net external forces. You're not still running your motor and revving it. There's not a rocket engine in the system. You don't have an outside source of energy. Such examples would include frictionless surfaces. Curling ice is a beautiful example of a nearly perfect closed system because curling ice is nearly frictionless. Systems in deep intergalactic space would be a good example of a closed system. Come on in. Pause the video for 1 second. So in deep intergalactic space, no friction. And by deep intergalactic space, I mean, Courtney, you're away from any planets. No gravity. Okay, that'd be an example of a closed system. Turns out, actually, systems floating on the water are a closed system. I'll show you a lovely video in a couple of days of that. And rolling objects. We're going to be looking for the next couple of days at collisions that are closed systems, that there's no outside external forces. Okay? So, for collisions in a closed system, first of all, the contact forces, Rebecca was correct, are governed by Newton's third, forces come in pairs. And I'm going to argue that the time is the same. I'm just going to argue everything's in an opposite direction. So here's my argument. I said in this car versus truck collision, force 1 equals negative the opposite direction of force 2, but the same magnitude. And since they're both the same time, I said if I multiply both sides by time, that time is the same. I'm not changing the equation. I'm just making it look different. What is force times time? Change in momentum or impulse. What I'm going to argue, Megan, is that in a car crash, in a head-on collision, the impulse, the change in momentum are equal but opposite. Huh? Let me show you what I mean. If the car loses 20 units of momentum, what happens to the truck? If the car loses 10,000 kilogram meters per second, the truck gains 10,000 kilogram meters per second. Now these are vectors, they're in opposite directions, so we could call one positive, one negative. Okay. Since momentum change is equal and opposite, the total momentum before and the total momentum after are the same. Momentum is not gained or lost, it's transferred from one to the other. We say that momentum is, here is a hugely important physics word, conserved. Conserved. When I say that something is conserved in physics, what I'm saying is you didn't lose anything. The amount before and the amount after are identical. One may have gained, the other one had to have lost the same amount. And then you can turn the page. Wait a minute, Mr. Dewick. What, Sheldon? Sheldon, in example 4, in this car crash, in this collision, what's the final velocity of the truck? What's the final velocity of the car? What's the final momentum of the truck? What's the final momentum of the car? So afterwards, what's 0 plus 0? So what's the total momentum afterwards? What's the total momentum before? How can you say that stuff's moving? Okay. This is our thought. Okay? I'm arguing that if the final momentum was 0, the initial momentum had to be 0. Let me prove it. Before the collision, Sheldon, what's moving? The truck, the car, both, or neither? Stuck together or separate? So I'm going to write this. Momentum of the truck initial and momentum of the car initial. Wham! They collide. After the collision, what's moving? The truck, the car, both, or neither? So what's the final momentum? So over here, that's got to equal 0 somehow. Now, I'm not saying that the car and the truck were stopped beforehand. Let's do an argument. Are you ready? Momentum is what times what? Anyone? Come on, people. Huh? I think you're right. Absolutely. So the momentum of the truck is going to be mass of the truck, V initial. Is that okay? And I'll put a little vector sign on the V. Plus mass of the car, V initial. You know what? I'll put a little C next to that, a little T, V initial of the truck, V initial of the car. Let's plug in some numbers. Sheldon, what's the mass of the truck? 24,000. I agree. 24,000, the mass of the truck? 2,400? Thank you. What's the velocity of the truck? Plus. What's the mass of the car, Sheldon? What's the velocity of the car? Please be careful. I'll give you a hint. It's not 24. What? Negative 24 meters per second. Have I been going on a vector rant the last couple of days about direction? Sheldon, in your head, what's 2,400 times 10? 24,000. In your head, what's 1,000 times negative 24? In fact, you get 24,000 plus negative 24,000. In your head, what's that? 0. I told you the initial momentum was 0. I didn't say they were at rest. I said the initial momentum was 0. They just happened to cancel each other out. Oh, and by the way, I cooked these numbers to make it work nice. If this had been, for example, 11 meters per second, really what that would have meant is after the collision, these guys still would have been skidding that way a tiny bit. There would have been a tiny bit of momentum left over in the positive direction. It would have looked like this. And that's what we're going to start to look at. It turns out with this notion, we can start to figure out missing velocities. This is really part of the physics of crash scene investigation. Connor, can you read to me this title?
The Law of Conservation of Momentum.
No, you read it wrong. You read it wrong. You should read it out like this. The law of conservation of momentum. It's a fundamental law of the universe. It's very deep. Thunder should rumble off on the horizon. Lightning should flash through the skies. A chill should go down in your spine. Your belly should tighten up in anticipation. This is the law of conservation of momentum. It is one of the laws that drives the universe. It's one of those laws that if we find something that contradicts it, we're willing to change our understanding of the universe rather than change the law. There's not many of those. What is the law of conservation of momentum? It says this: in any collision or explosion in a closed system, momentum is, here's our word, conserved. This means that momentum is not created. It's not destroyed. It means that the amount of momentum you started with has to equal the amount of momentum you ended with. It just means that it gets transferred from one object to another. The law of conservation of momentum can be written in several ways. It can be written in English. The total initial momentum of a system equals the total final momentum of a system. You folks have had me for most of a year. Do you think I'm going to write out the long English version ever? No. You could write it by saying the momentum of the first object initial and the momentum of the second object initial. Something happens, a collision or explosion has to equal the momentum of the first object final plus and the momentum of the second object final. You could use Trevor's notion that momentum is mass times velocity, and you could actually expand that. Give me 1 second, somebody phoning apparently. You could, Trevor, expand this out. Since momentum is mass times velocity, it's going to be m1 v1 initial, m2 v2 initial, m1 v1 final, and then you know that I tend to abbreviate. I tend to look for the shortest way to write it. I choose to use, and this is the one that's on your formula sheet, this one. Why? Because it's the shortest, and it lets me, Alicia, turn it into any other variation of this equation that I need. But it's got weird symbols, and so we need to talk about, does anybody know what that thing means? First of all, does anybody know what it's called? It's a Greek letter. Sigma. Nice nerd moment there. It's the Greek letter sigma. It is actually where our S ended up eventually coming from. Doesn't look much like an S. If you write it really fast, it sort of morphs into that kind of. This is how it's typewritten. Usually when you handwrite it, it just ends up being a capital M on its side. You don't add the stupid little and try and get it all nice and pretty. And it's an abbreviation. Does anybody know what it tells you, what it stands for? By the way, how many of you are planning on going to post-secondary someday? Okay, you will learn very quickly that there is a fairly universal abbreviation system that students have made up over the past 100 years or so. You'll notice sitting next to somebody that they have a shorthand in their notes. There are certain common words that we abbreviate. As an example, I know that, what do 3 dots mean? Do you guys know that one? Do you know what this means? Because it's the opposite of therefore. Like you pick up, people have all sorts of stuff, common words. And one of the common words is this one. So, going back to my rant, let me know what it means. It means the sum of, or the total. The total momentum before equals the total momentum after, which is exactly what I said the law of conservation of momentum was. This is sort of my starting point, almost like free body diagrams, get the obvious one, look, was for forces, almost like DFIC was for velocity, distance. This is my starting point, and I'll show you what I mean. First of all, I need to tell you, when do we use the law of conservation of momentum? We use conservation of momentum when there is an explosion or a collision. I'm going to say that again, but I'm going to emphasize something. We use it when there is an explosion or a collision. And the joke that I make is we use it when there is a jeune. You got a collision, you got an explosion, you got multiple objects. This is a job for conservation of momentum. There is some lovely examples of conservation of momentum, and one of them is a classic office toy called Newton's cradle. Let's apply this. We'll start off with little pictures, and then eventually we'll just go to word questions. Matt, what does example 5 want me to find? It says, find the...
Missing velocity.
In the picture, which velocity are we missing? Find the one that has a little question mark next to it.
VA.
Final or initial?
Initial. Final.
Why final? Because at the top of that little panel, it says the word after. Yes?
Yeah.
Okay, you ready? Here's my working through all of this. I'll pick on Matt because he's so much fun. Matt, is there a collision?
Yes.
More than one object?
Yes.
This is a job for conservation of momentum. So the first thing I write down is this. The sum of all the momentum beforehand equals the sum of all the momentum afterwards. That'll get you a mark or a half mark, depending on what the question is worth. Before the collision, Matt, what's moving? Mass A, mass B, both, or neither?
These are both
Stuck together before the collision or separate?
separate.
Yep. By the way, stuck together will be fairly obvious. Like here, I'll either write the word stick together, or the question will make it very obvious, okay? So I'll ask it again, not that you were wrong, but just to be stuck together or separate?
Separate.
So I'm going to write this. Momentum of car A initial plus momentum of car B initial. Wham! They collide. After the collision, what's moving? Car A, car B, both or neither?
Both moving.
Stuck together or separate?
Separate.
Momentum of car A final plus momentum of car B final. By the way, what if one of them wasn't moving? What would its momentum be?
0.
And I wouldn't even bother putting that particular term in. Okay? By the way, this looks like in the first situation, car A is going forward, and I guess car B is going in reverse. This is like a parking lot collision. Someone's backing out of a parking stall without looking. Okay? Momentum is what times what? What did Trevor say? Do you remember?
So velocity times mass.
Can we go mass times velocity?
Yeah.
Okay. So now I'm going to replace momentum A initial with mass A, velocity A initial. In your homework, you may reach the point, Alex, where you can start to take shortcuts and combine some of these steps. In our notes, I'll show every step. Plus, I guess it's going to be mass B, velocity B initial. Wham, they collide. Mass A, velocity A final, plus mass B, velocity B final. Is that okay, Court? Matt, what did you say they're asking me to find?
Velocity.
Which one? What's that? In other words, in this equation, what am I trying to find?
VAF.
Okay. I'll put a little dot above it so I can track it. I want to get that by itself. First, I need to move this over because this doesn't have velocity A in it. How will I move this thing over? Hey, what's sitting?
Subtract
Yep.
it.
Yep. So my next line, it's going to be MAVA initial. That just drops down like a domino. MBVB initial. That just drops down like a domino. I'm going to subtract the mass of B, velocity of B final. And that's going to equal the mass of A, VA final. Is that okay, Eric? Yeah. What did you say I'm trying to get by itself?
VAF
How would I get VAF, the velocity A by itself?
divided by MA.
Folks, do you mind? Can we do this all on this line without rewriting the whole mess? Okay. In other words, you want to know how fast car A is traveling after this collision? Okay. Car A is going to be mass A. How big is mass A, Matt?
Mass A is 1,000
Yep.
kilos.
Velocity A.
10.
I agree. Plus mass B.
2,000.
Velocity B. Don't say 2.
Negative.
Ah, we have to be careful and paranoid with directions, which is why I've been putting all those vector signs in to remind you. Let's just be careful. Minus mass B again, also 2,000. Velocity B final, positive 4 or negative 4?
Positive.
Yep. Now, I'm not going to give you pictures, Lydia, but I'll use words like east and west in a word problem, right? Divided by mass A, 1,000. Matt, if I get a positive answer, what direction will that be, left or right?
Right.
If I get a negative answer, what direction will that be? Yep. Good. Hey, is this a fraction? Yeah? Is there more than one thing on the top of the fraction?
Yep.
Brackets. Is there more than one thing on the bottom of the fraction?
No.
Don't need brackets. I would get my calculator out. I would get my calculator out. I think this will work out evenly because I see thousands and everything, and that's a nice number to times and divide by. Or if it doesn't work out evenly, it'll be like a nice decimal, like 1.3 or 2.9 or something. What'd you get?
I got negative 0.2.
Negative 0.2, I think is wrong.
Right, I might type that in wrong.
I think you get 1 point something, don't you?
Oh, after.
Negative what? Negative 2? Negative 2 even? Negative 2 going once? Anybody else? Negative 2? Negative 2? And I didn't type this in on purpose because too many of you are sponging on what I type it. So negative 2. So I'm going to write this, negative 2, and then I'll say 2 meters per second direction, Matt?
Left.
Left. Or we could have said west and east or whatever. I'll figure it out. Now, you could have let to the right be negative. Turns out you'll still get this right answer. You'll get positive 2, and positive 2, if you let right be negative, would still be left. All the numbers will take care of themselves. You'll have positives arrive negatives, you'll have negatives arrive positive, but in the end, we'll get the same answer. This is the law of conservation, of momentum. B. Courtney, is there a collision? Is there 2 objects? This is a job for the law of conservation of momentum. The sum of all the momentum beforehand equals the sum of all the momentum afterwards. Courtney, which velocity are they asking me to find? VA initial. Yeah. Okay. Before the collision, Courtney, my joy, what's moving? Car A, car B, both, or neither? Well, if car A wasn't moving, then it would have a velocity of 0. Would I really probably ask you to find that or not? So, before the collision, what's moving? Car A, car B, both, or neither? Both. Stuck together or separate? Before the collision, separate. One's backing in, one's driving forwards, but they're separate. Yeah, yeah? So I have this. Momentum of car A initial plus momentum of car B initial. Again, if one of them wasn't moving, its momentum is 0, and I just wouldn't write that. Makes my equation a little tidier. Bam! They collide. After the collision, what's moving? Car A, car B, both, or neither? Look at the little arrows in the picture. Both. Both. Stuck together or separate? Must be, because they're heading in opposite directions. Yeah, yeah. Oh, car A final and momentum of car B final. Momentum is what times what? Sure. Yep. So this is going to be, momentum A initial is going to be MAVA initial. Momentum of car B initial is going to be mass BVB initial. Wham, they collide. MAVA final plus MBVB final. Is that okay, Rye? Thumbs up. Court, which one are we trying to find? VA initial or initial, yeah? Is that what you said? Okay. This guy. I want to get it by itself. Need to move that over because that doesn't have the one that I want. How will I move that over? Yeah. Are you guys cluing into that whole formula manipulation? Because to try and give you every variation of this equation would have driven me crazy. So if I hear you correctly, and I think I do, you're telling me the MAVA initial kind of stays where it is. The right-hand side I'm going to rewrite, and then I'm going to subtract. Yeah? Mass AVA final plus mass Mr. Duick, mass BVB final, and I'll subtract mass BVB initial. Final step, Court, how could I get the VA initial by itself? Do you mind if I do that right now? And I will accept that, Rebecca, as showing your work. I don't mind being lazy and organized at the same time. Yeah, yeah? Okay, here we go, plug and chug. How fast must this car have been going? What was the mass? Oh, let's scroll up so I have my numbers. What was the mass of car A? Courtney, my joy. Yep. What was the final velocity of car A? 2? Okay. Plus, what was the mass of car B? 2000. What was the final velocity of car B? 4 would be wrong. Four would be wrong. This guy, but 4 would be wrong. And the reason it would be wrong is because of what you told me this was. What? That's not what you said. You said 2. So you decided that left is going to be positive. It's perfectly acceptable to do that. I mean, usually we let to the right be positive and to the left be negative, but you decided to let left be positive, then be consistent for the rest of the question. So don't tell me this is 4. This is going to be what? Yes, let's be consistent. It'll work. Minus mass of B, 2,000. What's the initial velocity of B? And please be very careful with the sign. 3, because you let left be negative. A little weird, but okay. Somehow suits you. Here we go. Divided by the mass of car A, which is 1,000. So if I get a negative answer, Courtney, that's going to be left. If I get a positive answer, it's going to be right. I think it is coming in. I think it's coming into the right from the picture. I think I'm expecting a positive answer, but maybe not. Right? Because the arrow in the picture is pointing that way. What do you get? Sorry, what'd you get? 4? Anyone else? You need to practice typing these in, boys and girls. And it's easier if you do it right away instead of me pausing, wasting 30 seconds of your time, and then cajoling you into typing these in, boys and girls. We have a 4. Anybody else get a 4? Oh, okay. 4 doesn't seem to be right. What'd you get? 12? Anybody else get a 12? Positive or negative?
Positive. Well, I did mine the other way, so I don't have 12 right.
So if we used Courtney's for my question here, would we get negative 12 meters per second or 12 meters per second to the right? The only thing I would be fussy on, if you said negative 12 to the right, I would take a half mark off, because what's negative right, technically? I would argue it's left. I'm going to do one more. Let's do one where they stick together. Just like best friends. Okay. Hey, Sarah, is there a collision? 2 object, more than 1 object? Sarah, what do they want me to find here? I think VA initial. Okay. Did I say there's a collision? Well, you know what? That's a job for the law of conservation of momentum. The sum, the total of all the momentum before has to equal the total of all the momentum afterwards. Now, in my notes, Alex, I'm writing every step. You may notice, Alex, that some of these steps are getting kind of repetitive. If you get comfortable enough in your homework to take some shortcuts in all of your writing and you're getting the right answer, I'm good with that. I would never take shortcuts, of course, on a test or a quiz. Right? Right. Before the collision, what's moving? Car A, car B, both or neither? Stuck together or separate? Okay. Wham! They collide. After the collision, what's moving? Car A, car B, both or neither? Stuck together or separate? Momentum both final, because they're stuck together. Okay. Momentum is what times what? So this is going to be mass A V A initial plus mass B V B initial. Wham, they collide. What do you think I'd write for the momentum of both? Plus. And I'll just call it V final. I won't say VA, or it's V final. Not, by the way, you said MAB. That would be times MA plus MB. The mass of both. What did you say I'm trying to find here, Sarah? Okay, now let's see how good we are. How would I get the VA by itself? What would I do?
Subtract the MB.
VB, and then after that, what?
Divide by
the mass of A. Feel like we can do that in one step? Feeling lucky? Yeah? Haley, we can pull this off? Let's do this. It's going to be this. So the velocity of A initial, Sarah said this stays where it is. I subtract that, and then you said, and then we'd end up dividing by that. Okay. This will work. The velocity of the incoming car was, what's the mass of A plus B? You know what? If you can do it in your head, go ahead. Otherwise, you'll just put the numbers there. But sure, 6,000. What's V final, Sarah? Now you've decided right is positive. Minus mass of B, 4,000. What's the velocity of B initial? Negative 3. Divided by 2,000. Basically, I can find any missing velocity if you give me the other masses and velocities. I can find whatever. This is the physics of car crash investigations. And in fact, usually you'd be interested in the initial velocity because the final velocity is usually 0. Just saying. Now, car crash investigations, Andy, are more difficult because it's not a closed system. As you skid, that force is also exerting an impulse, so you'd actually calculate mu times the normal the force of friction and how long that skid took, and you could actually work that into your equation as well. It's doable. I'm simplifying things. I should say I am dumbing things down a bit, okay? We can handle it. What'd you get? Sorry? 21 meters per second. Anybody else? Connor nods. Anyone else? 21? 21? 21 meters per second to the right. Okay. Falling off your bike? Yeah, we'll look at that. That's an example of a very slow collision, but there is a change in that works there. We'll also look at, then get into, instead of pictures, straight word problems. Curling is a great example. Already you can do, if you want to get a head start, you're capable of handling number 1. You're capable of handling number 2. You're capable of handling number 3. You're capable of handling number 4. You can handle 5 and 6. You can handle Calvin and Hobbes running towards each other, sticking together, or not. It's doable. But really, your homework is going to be, I'm about to give you a take-home quiz. And that's due next class.